Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 5, Alcohols. Alcohols are probably the most popular chemicals you'll encounter in organic chemistry. Ethanol has been popular with humans for more than 10,000 years. It's not just humans either. Many animals are known to seek out rotten fruits that have fermented enough to contain moderate levels of ethanol. Note that when we talk about consuming alcohol, we are referring to exclusively to ethanol, grain alcohol. In fact, consuming other alcohols can have drastically negative effects. Methanol, wood alcohol, for example, is oxidized by the body to formic acid, which is extremely toxic to the optic nerve and retina and can cause blindness when ingested. Isopropyl alcohol, commonly used as an antiseptic, can cause severe central nervous system depression. For organic chemistry purposes, of course, we do not restrict ourselves to only one type of alcohol. Many are used synthetically and in analytic techniques. Description and properties. Alcohols have the general formula ROH with the functional group OH referred to as the hydroxyl group. OH is hydroxyl. Nomenclature. Alcohols are named in the IUPAC system by replacing the E ending of the root alkane with the ending OL, all. If the alcohol is the highest priority functional group, the carbon atom attached to it receives the lowest possible number. Some examples are shown in figure 5.1. And we have 2-propanol with the OH on the second carbon. And we have 4,5-dimethyl-2-hexanol. So the 2 has the hydroxyl, and the 4 and 5 each have a methyl. Alternatively, the common naming practice is to name the alkyl group as a derivative followed by alcohol, as shown in figure 5.2. So here we have ethyl alcohol based off of ethane, and isobutyl alcohol based off of isobutane. When the alcohol is not the highest priority group, it is named as a substituent with the prefix hydroxy. Finally, we will also see that hydroxyl groups can be attached to aromatic rings, as in figure 5.3. These compounds are called phenols. The hydroxyl hydrogen of phenols are particularly acidic due to resonance within the phenyl ring. When benzene rings contain two substituents, their relative position must be indicated. Two groups on adjacent carbons are called ortho or simply O. Two groups separated by a carbon are called meta or M, and two groups on opposite sides of the ring are called para or P. Let's phenyl. Let's draw a phenyl here. Ring with some double bonds and an OH on top. We have the relative positions of the carbons. You have ortho, which is adjacent. We have meta, which is separated by one carbon, and para, which are opposite each other in the ring. So instead of writing this out, I'm actually going to draw this out. Ortho would be right next to each other. Meta would be separated by 1 carbon. And para are opposite each other. All right. Here we have O-bromophenol, and the bromine is 1 away from the hydroxyl. We have M-methylphenol, where the methyl group is 2 carbons away from the hydroxyl. And then we have P-nitrophenol, where the NO2 is opposite the OH. Physical properties. One of the prominent properties of alcohols is that they are capable of intermolecular hydrogen bonding, which results in significantly higher melting and boiling points than those of analogous hydrocarbons, as shown in figure 5.4. So I guess we just have 2 phenols hydrogen bonding in the way that water does. Molecules with more than 1 hydroxyl group show greater degrees of hydrogen bonding. This is evident from the boiling points shown in figure 5.4. So we have just an alcohol, a diol with an even higher boiling point, and a triol with an even higher boiling point. Should I also write that ring stabilizes the acidity? Nah. Also, these should have double bonds in them. All right. Hydrogen bonding occurs when hydrogen atoms are attached to highly electronegative atoms like nitrogen, oxygen, or fluorine. Hydrogen bonding is the result of the extreme polarity of these bonds. In the case of a hydroxyl group, the electronegative oxygen atom pulls electron density away from the less electronegative hydrogen atom. This generates a slightly positive charge on the hydrogen and slightly negative charge on the oxygen. Then the partially positive hydrogen of one molecule electrostatically attracts the partially negative oxygen of another molecule, generating a non-covalent bond force known as a hydrogen bond. The hydroxyl hydrogen is weakly acidic, and alcohols can dissociate into protons and alkoxide ions in the same way that water dissociates into protons and hydroxide ions. Table 5.1 gives the pKa values of several hydroxyl-containing compounds. So alkoxides are alkenes just with oxygen and not the hydrogen. And in this table, we have water at the top with a pKa of 14. This is not in order, though. So I take that back. It's not at the top. We have like tetrafluoro tetrafluoroethanol with a low pKa of 12.5. We have Fennel with a pKa of 10. So that would be the lowest. And tert-butanol, I guess, has the highest on this list with 17. And water's in the middle with 14. All right. Looking at table 5.1, we can see that the hydroxyl hydrogens of phenols are more acidic than those of other alcohols. This is due to the aromatic nature of the ring, which allows for the resonance stabilization of the negative charge on oxygen, stabilizing the anion. Like other alcohols, phenols form intermolecular hydrogen bonds and have relatively high melting and boiling points. Phenol is slightly soluble in water owing to hydrogen bonding, as are some of its derivatives. Because phenols are much more acidic than non-aromatic alcohols, they can form salts with inorganic bases such as NaOH. The presence of other substituents on the ring has significant effects on the acidity, boiling points, and melting points of phenols. As with other compounds, electron-withdrawing substituents increase acidity and electron-donating groups decrease acidity. Another trend in Table 5.1 is that the presence of more alkyl groups in non-aromatic alcohols produce less acidic molecules. Because alkyl groups donate electron density, they destabilize a negative charge. Additionally, alkyl groups help stabilize positive charges, explaining why more substituted carbocations have higher stability than less substituted carbocations. Which has a lower pKa, ethanol or p-ethylphenol? I would say that ethanol would have a lower pKa than phenol, because ethylphenol is a phenol, and its ring structure would stabilize the electrons for something like hydrogen to go and leave. Rank the following by decreasing boiling point: 1 pentanol, 1 hexanol, 1,6-hexanediol. Let's take a look at these a little closer. Number 2, 1 pentanol. So I guess this doesn't necessarily mean it's a ring. Are they saying it's a ring? It could just be but if it was, would that be aldehyde? Would that be pentaldehyde, rather? No, it's not a double bond. I guess you need a double bond. 1 pentanol. They don't have it in a ring structure. They just have it linear. So 1 pentanol, 1 hexanol, 6, and then 1,6-hexanediol. So 2 OHs. Since it's got 2 OHs to make hydrogen bonds, I would say that its boiling point would be the highest. And out of these two, since it's a negative charge we're trying to stabilize, more carbons won't help. So I bet this one would have a higher boiling point than the hexane. The pentanol would have a higher boiling point than the hexanol. So I'll rank these 1, 2, 3. Let's see how we did on that. 1. Phenols like p-ethylphenol have increased acidity due to resonance and the electron withdrawing character of the phenyl aromatic ring. Because p-ethylphenol is a stronger acid than ethanol, it will have a lower pKa. Is that what I said? Which has a lower pKa? I might have reversed it, but either way, the phenol is more acidic. I might have said higher pK. I meant lower pK. It's more acidic, has a lower pK. So also here, I might have reversed these with 10 being the most acidic, 17 tert-butyl being the least acidic. All right. Don't mess up the pKa. Low pKa is high acidity. Just like low pH is high acidity. All right. And then ranking these in order. The first was the 1,6-hexane diol. We'll have the highest boiling point. A molecule with 2 hydroxyl moieties can have more hydrogen bonding. The 1-hexanol boiling point will be next, the 1-pentanol having the lowest boiling point. 1-hexanol has a higher boiling point than 1-pentanol because the longer hydrocarbon chain has increased van der Waals forces. All right, so I was wrong about that. The carbons don't hurt. In fact, the carbons help. The longer chain makes for greater van der Waals forces. All right. Reactions of alcohols. The main reactions that we will see on the MCAT for alcohols include oxidation, preparation of mesylates and tosylates, and protection of carbonyls by alcohols. Oxidation reactions. Oxidation of alcohols can produce several products. Primary alcohols can be oxidized to aldehydes, but only by pyridinium chlorochromate, PCC, a mild anhydrous oxidant, as shown in figure 5.6. This reactant stops after the primary alcohol has been converted to an aldehyde because PCC lacks the water necessary to hydrate the otherwise easily hydrated aldehyde. With other oxidizing agents, aldehydes are rapidly hydrated to form geminal diols, which can be easily oxidized to carboxylic acids. So, primary alcohol to aldehydes. I guess more commonly to carboxylic acids. A primary alcohol with PCC makes an aldehyde. It stops halfway through its oxidation. Should I put in the geminal diol part in there? Primary alcohol first becomes a geminal diol and then a carboxylic acid. Secondary alcohols can be oxidized to ketones by PCC or any stronger oxidizing agent. Tertiary alcohols cannot be oxidized because they are already as oxidized as they can be without breaking a carbon-carbon bond. So let's put in a secondary alcohol. With anything, we'll make a ketone. So the difference between an aldehyde and a ketone is just that the ketone is in the middle of an alkane and the aldehyde is on the end, on a terminal carbon. So the oxidation of primary alcohols with a strong oxidizing agent like chromium will produce a carboxylic acid. In the process, chromium is reduced to chromium 4 is reduced to chromium 3. Common examples of chromium-containing oxidized agents include sodium and potassium dichromate salts like Na2Cr2O7 and K2Cr2O7. As with other strong oxidizing agents, these will fully oxidize primary alcohols to carboxylic acids and secondary alcohols to ketones. As shown, an example is shown in figure 5.7. And we have the oxidation of an alcohol to a ketone by dichromate salt. Finally, an even stronger chromium-containing oxidizing agent is chromium trioxide, CrO3. When dissolved with dilute sulfuric acid and acetone, this is called the Jones oxidation, as shown in figure 5.8. As expected, this reaction oxidizes primary alcohols to carboxylic acids and secondary alcohols to ketones. And we have the Jones oxidation of an alcohol to a carboxylic acid. So let's write down some oxidizing agents. Oxidizing agents include chromium, in a salt form. So Na2Cr2O7, K2Cr2O7, and apparently CrO3, chromium trioxide, in sulfuric acid and acetone. Why does it need acetone? Does it need ketones to oxidize an alcohol? I wouldn't think it would. Also, the chromium examples are in H2SO4, sulfuric acid. That's probably important. I'm going to put solvents here as well in blue. What else do we have? We have Jones oxidation, which is CrO3 with H2SO4 and acetone. Which is C3H6O. All right. Mesylates and tosylates. Spelled MESYLATES and TOSYLATES. The hydroxyl groups of alcohols are fairly poor leaving groups for nucleophilic substitution reactions. However, they can be protonated or reacted to form much better leaving groups called mesylates or tosylates. A mesylate is a compound containing the functional group SO3CH3, derived from methane sulfonic acid. Its ionic form is shown in figure 5.9. And we have two double bonds between the sulfur and oxygen, one single bond with another oxygen that's got a negative charge on it, and another bond to a methyl group. So let's write these down. The mesylate is the SO3CH3, and the tosylate we'll get to in a minute. Mesylates are prepared using methyl sulfonyl chloride and an alcohol in the presence of a base. Tosylates contain the functional group SO3C6H4CH3, derived from toluene sulfonic acid. These compounds are produced by reactions of alcohols with p-toluene sulfonyl chloride, forming esters of toluene sulfonic acid. A tosylate is shown in figure 5.10. And we see that it's somewhat similar to the mesylate, except instead of just a methyl group on it, there's this toluene, I guess. It's a methyl benzene. Just the ring part is the benzene, with the methyl group makes it toluene, and with the sulfur and the oxygens we get tosylate. SO3C6H4CH3. Now when you get up there with the C6s, it's kind of just better to draw it, right? It's just better to draw a ring. It kind of conveys more information at that point. In addition to making hydroxyl groups of alcohols into better leaving groups for nucleophilic substitution reactions, mesyl and tosyl groups can also serve as protecting groups when we do not want alcohols to react. These groups are protective in that they will not react with many of the other reagents that would attack alcohols, especially oxidizing agents. Thus, reacting an alcohol to form a mesylate or tosylate is sometimes performed before multiple step reactions in which the desired products do not derive from the alcohol. So let's write that they protect hydroxyl groups. Protecting groups. Alcohols can be used as protecting groups for other functional groups themselves. For example, aldehydes and ketones can be reacted with two equivalents of an alcohol or a dialcohol, forming acetyls, primary carbons with two OR groups and a hydrogen atom, or ketones, secondary carbons with just two OR groups. Carbonyls are very reactive with strong reducing agents like lithium aluminum hydride. Acetyls and ketones, on the other hand, do not react with lithium aluminum hydride. The acetyl or keto functionality thereby protects the aldehyde or ketone from reaction. After reducing other functionalities in the molecule, the acetyl or keto can be reverted back to carbonyl with aqueous acid, a step called deprotection. These reactions are shown in figure 511. And we have the what would happen if we didn't protect the ketone. Lithium aluminum hydride would reduce it to an alcohol. But if we protect the ketone with, I guess, an acetyl, by ketyl formation, so this is a ketyl, so we protect the ketone with a diol to make a ketyl that doesn't react with lithium aluminum hydride. We get the other functional group that we were targeting. In this case, the is that an ester? That's a carboxylic acid. Anhydride, what is this? COOH, but then this is also an ester. Either way, once we get that reduced, then we use a catalyst to remove our diol. So, ketones and, I guess I should say acetals, acetyls and ketones protect ketones, or aldehydes and ketones from reduction like by lithium aluminum hydride. Protect aldehydes and ketones from reduction like by lithium aluminum hydride. And then also there is deprotection at the end. What will happen to primary and secondary alcohols respectively in the presence of strong oxidizing agents? Primary alcohols are oxidized into carboxylic acids, and secondary alcohols are oxidized into ketones. How can primary alcohols be oxidized to aldehydes? Using a reagent like PCC will oxidize the alcohol but not the diol. Sorry, not the diol. It'll oxidize a primary alcohol into an aldehyde. What is the purpose of a mesylate or a tosylate? Mesylates and tosylates protect hydroxyl groups from being oxidized. And how can aldehydes or ketones be protected using alcohols? A diol reacted with an aldehyde or a ketone can make either a ketyl or acetyl, which is not reduced easily. Should we check the answers? In the presence of a strong oxidizing agent, primary alcohols are completely oxidized to carboxylic acids. Secondary alcohols can be oxidized to ketones. Number 2, primary alcohols can only be oxidized to aldehydes using pyridinium chlorochromate, PCC. 3, mesylates and tosylates are used to convert an alcohol into a better leaving group. This is particularly useful for nucleophilic substitution reactions because to increase the stability of the product, they can also be used as protecting groups because many reagents, especially oxidizing agents, that would react with an alcohol cannot react with these compounds. So they convert alcohols, hydroxyls, into better leaving groups. All right. Aldehydes or ketones. Number 4, aldehydes or ketones can be reacted with 2 equivalents of alcohol or a diol to form an acetyl or ketyl. Acetyls and ketyls are less reactive than aldehydes and ketones, especially to reducing agents. It can thus protect the functional group from reacting. The acetyl or ketyl can then be reverted back to carbonyl by catalytic acid. All right. So don't forget that mesylates and tosylates can be used in reactions as well. All right. 5.3, reactions of phenols. Reactions of phenols proceed in similar fashion to reactions of alcohols. However, as discussed previously, the hydrogen in the hydroxyl group of phenols is particularly acidic because the oxygen-containing anion is resonance stabilized by the ring. Quinones and Hydroxyquinones. Treatment of phenols with oxidizing agents produce compounds called quinones. Quinones are named by indicating the position of the carbonyls numerically and adding quinone to the name of the parent phenol. Due to the conjugated ring system, these molecules are resonance-stabilized electrophiles. Remember, however, that these are not necessarily aromatic because they lack the classic aromatic conjugated ring structure. So the double bonds are no longer on every other carbon. So they are not aromatic. Some quinones do have an aromatic ring, but this is not always the case. Quinones serve as electron acceptors biochemically, specifically in the electron transport chain in both photosynthesis and aerobic respiration. Vitamin K1 is the common name of the quinone 2-methyl-3 2E371115 tetramethylhexadec 2 and 1-il naphthoquinone. Wow. Shown in figure 5.13. This molecule is also called phylloquinone and is important for photosynthesis and the carboxylation of some of the clotting factors in blood. Vitamin K2 similarly corresponds to a class of molecules called menaquinones. So, I guess quinones are just a ketone on a ring. You take a phenol, you react the hydroxyl group to make a ketone. You oxidize the hydroxyl group to make a ketone. So I guess just a ketone on a ring is what we're calling a quinone. Hydroxyquinones. So phenol is an aromatic, but the product might not be. So they serve as electron acceptors. In photosynthesis and aerobic respiration, we have vitamin K1, which has a huge name, but is commonly called phylloquinone. Similarly, vitamin K2 is known as menaquinone. And that might be an important structure to know. But I doubt you'd have to memorize it. That's going to be a little bit of a challenge to memorize, right? All right, these molecules can be further oxidized to form a class of molecules called hydroxyquinones. Hydroxyquinones share the same ring and carbonyl backbone as quinones, but differ by the addition of one or more hydroxyl groups. Many hydroquinones have biological activity, and some are used in the synthesis of medications. One classic example is shown in figure 5.14. And this is hydroxybenzoquinone. So I guess what makes a hydroxyquinone is just an OH somewhere. That looks great. Now, I don't know if you could have a quinone with just one oxygen. It probably has to have two, because you probably can't just add one. You'll have like an odd number of electrons in the ring, right? Let's just put this other guy on here. Fill it in a little bit. All right. Now this quinone doesn't have two double bond. Oh, this is a double bond here. All right. All right. Because of resonance, hydroxyquinones behave like quinones with electron-donating groups, making these slightly less electrophilic, although still quite reactive. When naming these compounds, the position of the hydroxyl group is indicated by a number, and the total number of hydroxyl groups, if there is more than one, is indicated by a prefix, such as di or tri. With the substituent name hydroxy, several examples are shown in figure 515. We have tetrahydroxybenzoquinone, tetrahydroxy, 4 hydroxyl groups, benzoquinone. We have 5-hydroxynaphthoquinone. And then we have 1,2-dihydroxyanthraquinone. 1,2-dihydroxyanthraquinone. All right. It's a little less reactive than the quinones. So while we talked about quinones being electron acceptors biochemically, here quinones have electron donating groups. Are electron donating groups what makes it an electron acceptor? I wouldn't think so. What is an electron donating group? Electron donating group has the net effect of increasing electron density in a molecule through the carbon atom it is bonded to. Electron donating groups make nucleophiles stronger. All right. Next we have ubiquinone. Ubiquinone. Ubiquinone is one example of a biologically active quinone. Ubiquinone is also called coenzyme Q. Coenzyme Q. And is a vital electron carrier associated with complexes 1, 2, and 3 of the electron transport chain. Let's write down electron carrier in ETC. Ubiquinone is the most oxidized form that this molecule takes physiologically. It can also be reduced to ubiquinol upon the acceptance of electrons as shown in figure 516. This oxidation reduction capacity allows the molecule to perform its physiological function of electron transport. So we have ubiquinone, ubiquinol. Ubiquinone would be a ketone. Ubiquinol would be turning those ketones into alcohols, into hydroxyls. Ubiquinol is the reduced form. The long alkyl chain of this molecule allows it to be lipid soluble, which allows it to act as an electron carrier within the phospholipid bilayer. Other biological molecules that undergo oxidation-reduction reactions as part of their normal function include NADH, FADH2, and NADPH. These molecules accept and donate electrons readily, similar to ubiquinone, and are discussed more thoroughly in Chapter 9 and 10 of biochemistry. So although these are not quinones, we'll just put like NADH, FADH2, and NADPH. All right, how are quinones generally produced? Quinones are produced by oxidation of phenols. Oxidation of phenols. How are hydroxyquinones produced? By oxidation of quinones. What chemical properties of ubiquinone allow it to carry out its biological functions? Chemical properties of ubiquinone is that it can gain and lose electrons easily. So it can transport electrons. So I guess the gaining of electrons part is the reduction. It's easily reduced and oxidized. Thus, it carries electrons. It also has a long chain that allows it to permeate the phospholipid bilayer. So it is able to carry electrons across that membrane. Let's see how they answer. Quinones are produced by oxidation of phenols. Hydroxyquinones are produced by the oxidation of quinones. Ubiquinone has conjugated rings which stabilize the molecule when accepting electrons. Additionally, the long alkyl chain of the molecule allows for lipid solubility, which allows the molecule to function in the phospholipid bilayer. Sorry, not to cross the phospholipid bilayer, but to function in the phospholipid bilayer, to stay in there and not get pushed out. All right. Now some practice problems. Number 1. Alcohols have higher boiling points than their analogous hydrocarbons because the oxygen atoms in alcohol have shorter bond lengths. Hydrogen bonding is present in alcohols. Alcohols have more acidic and their analogous hydrocarbons. Alcohols can be oxidized to ketones. The reason that they have higher boiling points is hydrogen bonding. 1B. 2. Tertiary alcohols are oxidized with difficulty because there's no hydrogen attached to the carbon with the hydroxyl group. There's no hydrogen attached to the alpha carbon of the carbonyl. Tertiary alcohols contain hydroxyl groups with no polarization. They are relatively inert. Tertiary alcohols, so primary alcohol, secondary, tertiary. What is a tertiary alcohol? Tertiary alcohol. Primary alcohol, secondary alcohol, tertiary alcohol. So primary alcohol is attached to a carbon that's attached to 2 hydrogens, while a secondary alcohol is attached to a carbon with only 1 hydrogen. A tertiary alcohol is attached, a tertiary hydroxyl is attached to a carbon that has no hydrogens. There's no hydrogen attached to the carbon with the hydroxyl group. This is true. There's no hydrogen attached to the alpha carbon of the carbonyl. So alcohols don't have to have carbonyls. Those are ketones and aldehydes. Tertiary alcohols contain hydroxyl groups with no polarization. I don't know if that's true. They are relatively inert. Also, that may be true, but that is not what the question is talking about. There's no hydrogen attached to the carbon with the hydroxyl group. The main carbon we're talking about. Not the alpha carbon. Alpha carbon would be, like in a carbonyl. So, it's got to be A. 3. The IUPAC name of this molecule is, let's see, 1, 2, 3. 3 carbons, 2 hydroxyl groups. On the 1 and the 2. So this would be ethane, 1, 2, 3, no, propane, 1,2-diol. That looks good to me. Propanol, what's dipropanol? Does dipropanol not mean the same thing? But it's just not IUPAC. Propanol. All right. 3B. 4. The IUPAC name of this molecule is, well, we got a benzene ring, we got the OH, so it's a phenol, and we have a methyl group on the 3. So this would be in our MP ortho-meta para, this would be meta. So we go with M-methylphenyl. 3-methyl-cyclohexanol. It's not cycloheptanol, it's phenyl because they're double bonds. But yeah, M-methylphenyl sounds good to me. 4B. 5. Which of the following correctly lists methanol, isobutyl alcohol, and propanol by decreasing boiling point? Decreasing boiling point. Methanol is probably on the end. Propanol is 1, 2, 3. Isobutanol. Propanol. So you got our that is propanol, but let's do methanol first. Just 1 carbon and 1 OH. Carbon, OH. Simple methanol. Isobutyl alcohol. Propanol, 1, 2, 3, and then an OH. So the most van der Waals forces on the butyl alcohol, isobutyl alcohol, followed by propanol, followed by methanol. I'm going to go with C. Does this look funny if you just draw it like this? OH. All right. Number 6. Which of the following correctly lists hexanol, phenol, and cyclophenol by increasing acidity of the alkyl hydroxyl hydrogen? The greatest acidity has to be the phenol. Hexanol is just hexanol, just 1, 2, 3, 4, 5, 6 with an OH. So that's just a long chain. The phenol has the double bonds. Cyclohexanol looks like phenol but without double bonds. Is that all? Hexanol, phenol, and cyclohexanol. Increasing acidity. So the lowest would have to be the straight chain. That's not even an option. The only options are phenol or cyclohexanol. Increasing acidity. We know phenol is acidic. So how about cyclohexanol, hexanol, and then phenol? Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This has 12 hydrogens on it. Whoops, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So since this has more hydrogens on it for hydrogen bonding, I'm going to say, yeah, the straight chain hexanol has a higher boiling point than the cyclohexanol. So let's go cyclohexanol, hexanol, phenol. No, we're not talking about boiling point. We're talking about acidity. So what will affect the acidity? Protecting the electron withdrawing groups. Yeah, it's still going to be phenol on the right with the most acidity. So cyclohexanol, hexanol, phenol. Still gets the winner. All right. Number 7. Which of the following will convert CH3CH2CH2OH to CH3CH2CHO? So they say CH3CH2CH2OH to CH3CH2CHO. So this would be like an H and probably a double bond. So what'll turn an alcohol into an aldehyde? PCC would do it. The others are too strong oxidizers. I say 2 is the only one. PCC is the only one that could do it. Seven. It's got to be B. 8. Which of the following will convert cyclohexanol to cyclohexanone? An alcohol to a ketone. Cyclohexanol, the alcohol, is like a secondary alcohol. A secondary alcohol? Yeah, a secondary alcohol with one hydrogen bond, two carbon bonds, right? So a secondary alcohol turns into a ketone with an oxidizing agent like chromium trioxide, pyridinium chlorochromate, and sodium dichromate. I think all three would do the job. 1, 2, 3. 8's got to be D. Successfully converting 3-phenylpropanol to 3-phenylpropanoic acid by the Jones oxidation requires the oxidizing agent, the solvent, and dilute sulfuric acid, dilute sodium hydroxide, and hydrous conditions or high temperature. I guess it was sulfuric acid. H2SO4. Wrong, along with acetone. So I guess acetone's the solvent. CrO3 is the oxidizing agent. H2SO4. I think it's A. Is it sulfuric acid because it's anhydrous? Or is it just a requirement? When dissolved with dilute sulfuric acid and acetone, this is called the Jones oxidation. They don't get into it, but they're pretty clear that it's the dilute sulfuric acid. 10. Treating 2-methyl-1-propanol with methyl sulfonyl chloride in base, followed by reaction with pyridinium chlorochromate, and a final step in strong acid will give an end product of. All right, so treating propanol, 1, 2, 3 is propanol, 2-methyl-1-propanol with methyl sulfonyl chloride in base, followed by reaction with pyridinium chlorate. So what is methyl sulfonyl again? Methyl sulfonyl was one of our protecting agents. Methane sulfonic acid, methyl sulfonyl is one of these. Methyl sulfonyl. Sorry, methyl sulfonyl is right here. Methyl sulfonyl chloride, so a Cl on it, Mesylates are prepared using methyl sulfonyl chloride and an alcohol in the presence of a base. So, the alcohol is the propanol. Methyl sulfonyl chloride in base will produce a mesylate. And then once we have the mesylate, followed by a reaction with pyridinium chlorochromate, and a final step in strong acid. So the question is, are we using this mesylate to protect this OH or to react it? To make OH a good leaving group? Either way, what we're trying to do is oxidize this into a aldehyde. PCC usually takes alcohols to aldehydes. So why do we need this methyl sulfonyl chloride in here? Well, the options for answers are 2-methyl-1-propanol, so no change. Is that what would happen? Would you protect the hydroxyl group and so it wouldn't react, it wouldn't oxidize? Right? Is that what it does? It protects it from oxidation? Groups are protective in that they will not react with many of the other reagents that would attack alcohols, especially oxidizing agents. So basically, we're protecting it from the oxidizing agent, and then we're just removing it. So I guess you could say, yeah, I guess no change in the end. 2-methylpropanol, 2-methylpropanoic acid, 2-methyl-1-propane. Propanol is the aldehyde. But yeah, I think it makes hydroxyl groups into better leaving groups for nucleophilic reactions, but for oxidation reduction reactions, it will protect the hydroxyl group. So in this case, I think all that ends up happening is you get the same thing that you started out with. A. 2-methyl-1-propanol. 11. Reaction of 1-phenylethanone, 1-phenylethanone with ethyl glycol Also known as ethane 1,2-diol. An aqueous H2SO4 will result in the formation of, I bet it's going to be a ketol. Reaction of 1-phenylethanone. 1-phenylethanone. Fennel, phenylethanone. So phenyl and then ethane, ethanone, ketone. Also called acetophenone. Is that right? All right. 11. Reaction of 1-phenylethanone with ethylene glycol, which I think is a triol or diol. Ethylene glycol. So it's a diol, not a triol. Diol. Ethylene glycol. Ethylene glycol. HO 1, 2, 3, 1, 2, 1, 2, and then an OH. So just 2 carbons. Ethane 1,2-diol. An aqueous H2SO4 will result in the formation of So let's look back at the diol and see if it looks similar. Where are the diols? Is that not even in this chapter? Well, I guess this one is what we're looking at. This is our diol. This almost looks like the same molecule, except what we were protecting was a ketone. Here, the ketone is over here. But this is what we're protecting. This ketone is what we're going to protect. So these will make something like and then this will have our O, O, look something like that. So that's a ketol, not an acetyl, I think. Hemiacetyl, that's a ketol. 11A. 12. Treatment of this molecule with CrO3 under appropriate reaction conditions will yield which of the following molecules? So CrO3 is an oxidizing agent. I believe the OH, the hydroxyl group here, will be oxidized to a carboxylic acid, I guess. Why not all the way? Primary alcohol, so it'll be a carboxylic acid. It'll be phenylethanoic acid. It won't be an aldehyde, a ketone, or an alcohol. It'll be the acid, 12D. 13. In order to convert phenols into hydroxyquinones, how many steps of oxidation or reduction are required? Well, let's take a look. Fennel, one step to the quinone, and then another step to the hydroxyquinone. So 2 oxidation steps. 13 is going to be B. 14. The conversion of ubiquinone to ubiquinol requires what type of reaction? Ubiquinone to ubiquinol. Do we do this? I didn't draw a picture of this. But ubiquinone to ubiquinol is reduced. Reduction. 14, C. And 15, which of the following will convert a cyclic acetyl to a carbonyl and a dialcohol? A cyclic acetyl back into a ketone and the diol. So basically, how do you undo this protecting? Let's take a peek. They use a catalyst, H+, H2O, so acidic conditions. Aqueous acid, that sounds good to me. LiAlH4 is the reduction part. CrO3 is oxidizing. And acetone is not even in this reaction. Aqueous acid, 15A. Let's see how we did. Number 1 is B. 2 is A. 3 is B. 4 is B. 5 is C. 6 is B. 7 is B. 8 is D. 9 is A. 10 is A. 11 is A. 12 is D. 13 is B. 14 is C, and 15 is A. Got them all right. Good job. All right. That is it for alcohols. Next time we'll get into aldehydes and ketones, part 1, electrophilicity and oxidation reduction. Thanks for watching. I'll see you next time.